Welcome to Economics 1723 Capital Markets. This is the second part of the online module for Lecture 14. We're talking about bond concepts. We're going to cover duration and convexity in this part. So I'm going to start with a concept known as Macaulay's duration, after a guy called Frederick Macaulay who wrote in the 1930s. So let me introduce the concept. We've seen already that the sensitivity of the price of a zero coupon bond to its yield, its YTM, its yield to maturity, depends on the maturity of the bond. Basically, a longer term bond has a price which is much more sensitive to yield than a shorter term bond. Now what we'd like to do now is generalize this sensitivity analysis to cover coupon bonds. Remember, with a coupon bond, some cash flows arrive earlier, these are the coupons, and some arrive later. There's a final coupon and then the face value. So intuitively, you would think that the effective maturity of this bond is some kind of average of the maturity of these cash flows. In other words, it's an average of the lengths of time until each of these cash flows is paid. The question would be then, how do we form this average? So Frederick Macaulay had the clever idea of calculating a weighted average of the times to each payment, where the weights are the present value of each payment divided by the price of the bond. So let's work this out a little more mathematically. Think about an M period bond, which is going to make payments in each period from 1 to little m. So let's pick one payment that's going to be made in period capital M. That could be, let's say, 2 periods from now or 3 periods from now. And the number 2 or 3 is going to be weighted by Wm. This is the weight on the M payment, which is going to be the present value of the payment divided by the price. Now, when we calculate that present value of the payment, we're going to take the amount, the dollar value to be paid, payment M, and we're going to discount it using the bond's yield. So we'll divide by 1 plus y to the power m. All right. So having defined the weights this way, then the duration of the bond is going to be duration d is the sum across all the payment times, distance from the present, 1 through little m, of the length of time to the payment times the weight on that payment. Okay, so it's a weighted average of the lengths of time until each payment is made. All right, so here's an example, a nice illustration in the Bodie-Kane-Marcus book. So suppose we have a 9% coupon bond, which pays coupons annually, and the bond has 8-year maturity, and let's suppose the yield to maturity is 10%. All right, so the height of each bar is the total of interest and principal. And for the moment, look at both the hot pink and the pale pink. So we're just calculating the total amount to be paid in each period. And, that's going to be with a face value of, so it's got a face value of $1,000. So it's paying 9% annually. So it should be paying $90 it should be paying $90 every year, so that's this stream of $90, and then at the end it should be paying $1,090, okay, which is this big bar at the end. All right, now what the hot pink shows is the present value, okay, discounting at 10% a year. So for the first year we just divide by 1.1. And for the second year, we divide by 1.1 squared, 1.1 cubed, and so on until we get out to 1.1 to the 8th. So you can see that the hot pink bars are a declining fraction of the total hot and pale pink bars as we go further out. All right, now what we're going to do is take a weighted average of these numbers, 1, 2, 3, 4, 5, 6, 7, 8, where the weights are these hot pink bars. You could think of that as, in a physical sense, if this was a piece of wood on which you had metal weights of these sizes, and then you were balancing the piece of wood, where would it balance? It would balance at about 6, just under 6, 5.97 years. because this big weight to the right just offsets these small weights to the left. Okay, so that's the physical analogy, but essentially what you're doing is you're averaging these numbers using the pink bars as weights. Of course, the weights are, you divide by the sum of all of these, which is the price. Okay, so there's Macaulay's duration. Now, if you have a zero coupon bond, the duration is just equal to the maturity. Why is that? Well, let's go back. If you had a zero coupon bond, none of these bars would exist. There would only be this one, and of course, then the only way for this to balance is for the balance point to be right here. There's only one payment you're averaging, so this gets all the weight, and you'll just end up with the number 8. Okay, so that's for a zero coupon bond. Of course, for a coupon bond, you're always going to be shifting the balance point to the left. So for a coupon bond, duration is always less than maturity. And finally, there's a special case that's worth noting. For a perpetuity, duration can be explicitly solved as 1 plus y over y. In that case, there's an infinite stream of payments, but because we're weighting the times by present values and present values decline geometrically, there's an explicit solution, 1 plus y over y. So let's think about the properties of duration. It should decrease with a bond's coupon rate, because the higher the coupon, the more of the value comes from near-term payments. It should decrease with a bond's yield to maturity, because as the yield goes up, you downweight the more distant payments more, and thus you shift the weight to the nearer term payments. And finally, D generally, but not always, increases with a bond's maturity. It's pretty interesting to think, why doesn't it always increase with maturity? And I'll help you out. Let's go back and look at this. If you imagine increasing the maturity, you're doing a couple of things. You're going to insert a new payment and shift all these payments out by one period. Now, on the one hand, you're adding more payments, so stuff is shifting out. You would think that would increase duration, and generally it does, but there is an offsetting effect, which is that the big final payment is now discounted more, so the stream of small near-term payments gets a higher relative weight, and under certain circumstances that latter effect can dominate. So we're going to move back forward now to look at this figure from Bodie, Kane, and Marcus. This is plotting duration against maturity. If we have a zero coupon bond, that's just the 45-degree line, because duration equals maturity. For coupon bonds, these curves lie below the 45-degree line, showing you that duration is less than maturity. Now, if you compare the gray line and this blue line, you will see that when the yield goes up, the duration falls. But if you look at the dashed blue line, that's a case where there's a very low coupon and a very high yield, and that's exactly the circumstance where, as you increase maturity, it's possible for duration actually to decline. So you can see this blue dashed curve is actually hump-shaped. All right, now why do we care so much about Macaulay's duration? Well, the reason is that it gives us a generalization of the price sensitivity equation for zero coupon bonds, which, if you remember, is that dP over P, the proportional change in price, is minus maturity divided by gross yield times the change in the yield. Now, it turns out that this equation generalizes to coupon bonds once we replace maturity with Macaulay's duration. So we get dP over P equals minus D over 1 plus y dy. So what duration is doing is capturing the sensitivity of the bond price to changes in the yield, and it's important because it's a measure of bond risk. It captures the risk in the bond that's associated with changes in interest rates. And in this respect, it's similar to beta for a stock. Beta captures the component of risk that's associated with stock market movements. Duration captures the component of bond risk, which is associated with interest rate movements. Now, what practitioners often do is calculate something called modified duration. We'll write that D star, which is just duration divided by gross yield. Because then the previous equation simplifies. We get dP over P equals minus D star dy. So modified duration gives you the proportional change in price caused by a given small absolute change in the yield to maturity. So for example, if D star is 10, then a 1 percentage point increase in yield, say from 5% to 6%, causes a 10% drop in the price. And that calculation is very quick and immediate to do once you know the modified duration of a bond or of a bond portfolio. So here's an illustration. This again is from Bodie, Keane, and Marcus. We're looking at changes in yield to maturity, and we're looking at the percentage changes in bond prices. The blue line is the exact relationship, and the black dashed line is a linear approximation, which will be very accurate for small changes in yields. And the slope of this black dashed line is modified duration. Okay, so by calculating modified duration, you're calculating the local sensitivity of the bond proportion of the percentage change in the bond price to the change in the yield. Now notice, of course, that the exact relationship is nonlinear. Why is that? Well, as a bond's yield declines, the duration is going to increase. All right, why? Because first of all, we're dividing by a smaller number, 1 plus y, when we calculate modified duration, and also there'll be the effect on Macaulay's duration for a coupon bond. So for both reasons, the modified duration of the bond is going to increase as the yield falls and decrease, flattening out this curve, as the bond yield increases. So over large intervals where interest rates are moving a lot, we need to take account of the fact that the modified duration itself is changing. But for small changes, we can ignore that. All right, so this gets us to the final topic, which is convexity, or curvature. So I've explained, I hope, why the curve in that diagram is convex. As yields fall, modified duration rises, so the curves get steeper on the left. And as yields rise, modified duration falls, so the curves get flatter on the right. And this property of bonds is known as convexity. It applies for both zero coupon and coupon bonds. For zero coupon bonds, it results purely from the dividing by 1 plus y component of modified duration. And for coupon bonds, it results from both components, Macaulay's duration and then the division by 1 plus y that gets us to modified duration. So what convexity says is that the bond's price after a yield change is always higher than predicted by the linear approximation. The blue curve is always above the black dashed curve. If you take that into account, it gives a more accurate approximation. In economic terms, what it says is that bonds benefit from volatility. So if there's a lot of volatility, there's downside risk and upside potential. The downside risk is limited by the decline in duration that occurs when yields rise, whereas the upside potential is very large and is driven by the extension in duration that happens when bond yields fall. Okay, so that's it for today, and we'll discuss this further in lecture. Thank you.